Hello everyone, welcome to my YouTube channel. So in this lecture, I will talk about the Diels Alder reaction. So in the previous lecture, I will give the brief introduction about the Diels Alder reaction, how the relative rate of the Diels Alder reaction is depend on the substitution on the dienophile or diene, or how the stoichiochemistry is maintaining the resultant reaction, how the substitution on the substitution position on the line affect the reaction rate. So in this lecture, I will teach about the regioselectivity of the Diels-Alder reaction. So regioselectivity refers to the orientation of a cycloaddition. So a question of regioselectivity arises when both the diene and dienophile are unsymmetrically substituted. Generally, there is a preference for ortho and para respectively as shown. So here, when the regioselectivity means when these both the diene and the dienophile are unsymmetrically substituted, here maybe so in this reaction, this diene and dienophile endoaddition to form this ortho-like product, and maybe the and here all this case maybe the para-like product. So this reference can be understood in terms of the counter-orbital theory. In the most common cases, the diene contains an electron donating group and dienophile contain an electron withdrawing group. Thus, the beta interaction is then when the homodiene and the lumodienophile. So that to explain the regioselectivity, we have to look the coefficient of the atomic orbital in the more important pair of the counter orbital. So this regioselectivity is controlled by the we can understand the regioselectivity in terms of the frontier orbital theory. So here mainly the electronic interaction between the HOMO of the diene and the LUMO of the dienophile, and the most common cases diene are the electron diene containing the electron donating substituted and dienophile containing electron withdrawing substitution. So let us consider this situation where the electron releasing group of the diene in one position and electron withdrawing group in the LUMO of dienophile to form this ortho-like product. So now, if we try to find the HOMO of the diene containing electron releasing group, it may be combination of two ideal systems, HOMO of the betadiene and HOMO of the pentadiene anion. So here, this is the HOMO of the betadiene and this is the HOMO of the pentadiene anion. So HOMO of the diene is the more so here electron donating releasing group, here is the more counter orbital contribution in this side. So again we know that the electron withdrawing increases the energy of the orbital. Thus we have the LUMO of the dienophile. This is the HOMO of the dienophile, this is the LUMO of the dienophile. Now considering the law of interaction, HOMO of the diene and the LUMO of the dienophile, we may have two products, but it is evident that the choice of the large interaction is better than the two large small interaction. So here, so that means here the most contribution on this orbital, and here for the small contribution on this orbital. So here these two large interaction will favor, so that will give the ortho-like product. And this large small interaction is disfavored, so the metal-like product is not formed, the ortho-like product is formed. So again we have another situation where the substitution of diene at C2 position. Thus the HOMO of the diene and LUMO of the diene give this only the para-like product. So if we find out the HOMO of the diene containing electron releasing group at C2, it may be combination of two ideal systems. the HOMO of the butadiene and HOMO of the allyl carbanion. So HOMO of the butadiene and HOMO of the allyl carbanion. So this is the combination. So HOMO of the diene is here. So here the electron mode orbital more electron contribution in this orbital. So again we know that electron will to decrease the energy of the p orbital. Thus we have the following LUMO of the dienophile is like that way. Here is more contribution. So here similarly the considering the loop, the interaction of the HOMO of the diene and the LUMO of the dienophile, we may have two products, but the evidence that the choice of the large interaction is better than the two large small interaction. So here these two large interaction is favored, that will give this parallel product, and this large small interaction is disfavored, so that will give the metallic product. So that's why the C2 substituted diene will give only the parallel product. Now Lewis acid catalyzed usually increase the reducibility of the reaction. So uncatalyzed case, this parallel product is a 70% and this metallic product is 30%. And for when the Lewis acid is present, the reducibility increases the 95% of the parallel body form. So obviously this is the agreement with the concept of contra-orbital theory. One we feel that we have the flavored hard to justify the reducibility of Diels Alder reaction. Any experienced organic chemist may predict the reducibility by using trial error in the following way. So here this is negative charge, this is positive or negative positive, so that will give ortho-like product with a favored one. And for this case, here the negative charge in this position, so here that's why the metallic product. So reasoning appear to find, but it can become applicable for all cases. For example, it does not work in the case of reaction between the butadiene and carboxylic acid and acrylic acid, where ortho-like product we get 90% and metallic product get 10%. But the Karl error indicate the ortho-like product cannot be main product, as then the positive charge or to be repel each other. So however, this selectivity can be explained by considering the coefficient of the atomic orbital in the more important pair of the frontal orbital. HOMO of the butadiene with the carboxyl can be considered the psi 3 of extra diene. So LUMO of the acrylic acid can be considered psi 3 of the butadiene. This is the LUMO of the diene. So we have the following observation. So we have large interaction in favor. So that's why it gives this ortho-like product. This large small interaction is disfavored, but the metallic product is not formed. So the anions of this acid also undergo Diels Alder reaction. Similar reasoning predicts that the ortho-like product will be the major product, but this time the negative charge on carboxylate anion will strongly repel each other. Thus the reward with the metallic attack. Actually, the observation 50-50 in favor of the ortho and beta anions. So the above study indicate that the Diels Alder reaction can be utilized to obtain the cyclohexane derivative with at least one electron withdrawing group on the far side of the ring. So obviously, this cyclohexane can be utilized to obtain 1,6 functional of the functionality of the unsaturation to design the synthesis with the fine disconnection approach. So here from this the butadiene and this alkene give this cyclohexane type molecule. So here consider the synthesis of this now. So here we may consider the electrosynthetic analysis. So here all are in cis 1,6 bifunctional group from this one, and this will remain an n by addition to give this. So here the following steps: cyclopeptide with this dienophile lead to n by addition product upon which is upon react with the alkaline KMNO4 and H3O plus, so give this product. So this is the synthesis procedure for this product. So now I'll discuss about the which of the following compound done this participate in the Diels Alder reaction and why? So first, this one will these three compounds is not participate in this Diels Alder reaction. Why? So this is a alkene time molecule. This is a 10-year, and here this time is in the S trans fashion, and here also this time is the S trans fashion. But we know that in the Diels Alder reaction, the time may should be in the S6 configuration. So here the S6 configuration is not possible for this all these three molecules. So hence these three molecules don't participate in the Diels Alder reaction. The next question is the complete the following. Here, these conjugated double bond are locked. So esters orientation, so they cannot participate in this cellular reaction. But here, this double bond are locked in the SS orientation. Thus, it will participate in the cellular reaction. So thus, this diene and this dienophile will be created to give this product. So here, say reduced certain coefficient in the terminal carbon are higher. In the homo of the hexadenine system, coefficient of terminal carbon of the dienophile bearing an electron withdrawing group. So next question is, a mixture of trans 2-hexadiene and the cis trans 2-hexadiene was allowed to react with the melanic anhydride room temperature. After the reaction, the precipitated disolar reduct can be filtered off. Unit unreacted diene was found to contain only one starting 2,4-hexadiene isomer, which isomer did not react. Explain. So here, this molecule has a two configuration. One is the trans and one is the cis trans. So in the cis configuration, cis trans, there is an unfavorable steric interaction as shown, but there is no such unfavorable steric interaction in the S trans. Thus, the cis trans isomer will try to remain in the S trans configuration. So cis trans isomer did not react in this reaction. Now the next question is, draw all the possible isomer of this molecule. Obviously, only one isomer participates in the reaction, and why? So this molecule has these three stereoisomer. One is trans, one is cis trans, and one is cis. So in this cis component, cis trans and this cis, there is a steric interaction with phenyl hydrogen, and here the steric interaction with phenyl pairing. So this is an unfavorable steric interaction. There is no such orientation in the, but in the trans there is no such steric interaction. So only this one is reacting in the Diels Alder reaction, and these two did not participate in the Diels Alder reaction. So here, for the S trans configuration, the most well is the S configuration. So here this diene S configuration and S trans configuration. Here the S configuration is not stable due to the steric interaction. So here S trans configuration of this diene is favorable. So thus here no reaction is happened between this diene and this dienophile. So now I will discuss about the Hofmann rearrangement or the Hofmann amide degradation. So Hofmann rearrangement in 1881 we discovered in of the conversion of the amide to the primary amine with one carbon less by the action of the alkaline hydrolyte or the Br2 or Cl2 on the alkaline condition. So Hofmann rearrangement mainly the amide to amine formation in period of NOx or the X2 is a under alkaline condition. So overall reaction is written as a R C double bond O NH2 in plus X2 plus NOH to form this amine plus NaX, Na2CO3 plus H2O, or the RCONH2 NOx plus 4 equivalent of NOH to form this RNH2, NaX, Na2CO3 and H2O. So obviously this reaction can be considered to be the oxidation of the halogen or by hypolite. This reaction is a unique technique to obtain pure primary amine. Here or maybe alkyl, aryl or heteroatomic unit. Let us consider the following reaction. So here the pimulic acid converted to the 3-dimethyl butonic acid in reacted with on SOCl2 and this azide and this silver salt, the Arnester synthesis to form this alcohol, and then again the reaction with the SOCl2 plus NH3 to form this amide. We react with this bromine Br2 in presence of alkaline NOH to form this amine. And here the didacamide in presence of Cl2 and NOH to form this nonan-1 amine. So this is the example of this Hofmann rearrangement. So benzoic acid in presence of Br2 FeCl3 to form this 3-bromobenzoic acid, which react with this SOCl2 reflux and NH3 to form this amide. And again this amide is react with this Br2 KNOH to form this 3-bromoaniline. And the patholic anhydride reflux in acetic acid in presence of NH2 CONH2 to form this amide, and then this Br2 NOH to form this aldehyde amine. Test with reacts with this acetate to form this anaphthalic acid. And here the 3-methyl pyridine in presence of aqueous alkaline caminophore to form this nicotinic acid with reflux with the ethanol and H2SO to form this ethylated one. Then NH react with NH3 to cut this from this amide with when this amide is in presence of Br2 and NOH to form this pyridine 3 amine. 2-fluoronicotinamide also react with the Br2 KOH to follow the Hofmann rearrangement to follow this 2-fluoropyridine 3 amine. So let us consider the mechanistic course of this reaction. So first step in the mechanism is the abstraction of an amide proton by the base. The resulting anion is then halogenated. So first step in the presence of base, this proton is abstracted to form this anionic intermediate. Next, there this arrow pushing to form this intermediate. Next, this bromine atom is attacked to form this intermediate. This reaction is very similar to the first step in the base catalyzed halogenation of ketone. The resulting N halogenated amide is within even more acidic than the amide starting material. It is 2 ionizes, so resulting anion, however, does not halogenate it again. For it, undergo even faster reaction, rearrangement to isocyanate. So here then, in presence of base, this brominated amide, this base abstract the photon to form this anion. Then this R group is migrated to this 9 and bromine elimination to form this isocyanate intermediate. To form this isocyanate intermediate, undergo alkaline hydrolysis to yield the primary amines and the carboxylate anion. So this mechanism code is supported by the following fact: a number of intermediates have been isolated in bromoamides are CONHBr, salts of these bromoamides. When the optically active alpha phenyl propioamide undergo Hofmann reaggregation, alpha phenyl ethylamine with retention in configuration is obtained. So here the alpha phenyl propioamide had the also the retention of the configuration to alpha phenyl ethylamine. Obviously, this proves the intermolecularity of the reaction during the migration. So again, further support regarding the intramolecularity of this reaction comes from the crossover experiment when this nitrogen atom is labeled. So here this amine is from known in meta 5, N5, M15 amine is here not formed, so no cross product is formed. So that proves that this is a intramolecular dating of this reaction. Originally, it is believed that a reaction proceeds by the formation of nitrogen intermediate in the following way. So here this nitrogen intermediate form upon elimination of this bromine, then this intermediate form. But when R equal to this, the rate of the reaction is changed in component in case of when R equal to this. So this rate of this reaction is changed when the R contains an electron donating group. This indicates the synchronous migration of R and elimination of Br. If the nitrogen to be intermediate, we expect the formation of R CONH, but this is not the case. So this is the overall the Hoffman reaction. So now I will discuss. So during this Hoffman reaction, side reaction are also formation ureas and acyl ureas by the addition respectively RNH2 and RONH2 and RCONO. So here from this isocyanate intermediate hydrolysis to form this amine. Here also this amine react with this intermediate to form this, and here also this intermediate react with this amide to form this. So if the acyl areas are desired, then it can be made product by using only half the usual quantities of Br2 and NOH. For this amide of high molecular weight, the yield is low, presumably due to their low solubility in the aqueous reaction condition. In a modification used for the high molecular weight, amide may be substituted by the aqueous NOH to form this methyl carbamate, which may be isolated or hydrolyzed. Thus, this amide reacts with this Br2 NCOC to form this intermediate, and then this amine is formed. So this modification avoids the possibility of the formation of ureas and the acyl ureas. So although the Hoffman degradation is a unique technique to obtain pure primary amine, it has been applied in different ways to obtain products other than the amine. Thus, alpha beta unsaturated acid or the alpha hydroxy acid may be degraded to carbonyl compound by the Hoffman method. So here this alpha beta unsaturated acid to form this alpha beta to amide. Again, this Hoffman reaction to form this amine, they is converted to the corresponding aldehyde. So it alpha hydroxy carbamide to form this amine intermediate. Next it goes to this aldehyde. So again, N-alkyl urea gives hydrogen and analogous reaction. Similarly, the manufacture of the hydrogen urea is treated with the alkaline sodium hypothalite to form this hydrogen molecule. So, however, the use of oxygen leads to the further oxidation of hydrogen to nitrogen. So now I will discuss some problem. So the result here, the first problem is many years before Hoffman degradation of radioactive alpha phenyl propionamide are studied. The following observations are made. So this reaction will be to form this amine with react to form this one. So here COH and CONH2 group switch to each other. What does result show about the mechanism of the reagent? So this result indicate that during the Hoffman reaction, the alkyl group migrate to the retention of configuration. So here this is formed. Again this and for Hoffman reaction on an amide to yield amine and carbamate ion on equivalent empirical, this will be clear from the oxidation number calculation. The next question is complete this following one. For the Huffman reaction, on an amide to yield the amine and carboxylate ion, one equivalent NOBr is required. This will clear from the oxidation number calculation. So the oxidation number of this is 0, oxidation number of this carbon is +3. So after Huffman rearrangement, the oxidation number of this carbon is +1, oxidation number of this is +4. So increase the oxidation number is +2. So NOBr oxidation number is +1 and NABr oxidation -1. So decrease in the oxidation number 2. So again, for the same reaction, 2 NaOH is consumed as obvious from the balance equation. So in the given problem, one equivalent NOBr is given excess during the reaction. So we do not further bromination on the aniline. Thus, this orthogonal substituted brominated product is formed. So the net balance equation is the NOBr plus NOH to form this brominated amine. So next question is the complete the following. Here this butyrate equivalent with bromine. So the given reaction sequence with the following steps. So first actamide reacts with the bromine on equivalent NOH to form this intermediate that react with this on equivalent of this amide to form this acetyl methylurea. Then upon the concentrated HCl, this N-methylurea is formed. Then reaction with the NO2 and HCl, this N-methyl in nitrosourea. Then 50% fluorine ether to form this diazomethane. So this is the way to obtain the diazomethane. So the next question is explain the following reaction mechanistically. Here this amide react with the PB acetate CH2 to form this amine. So here the reaction may be follow the following pathway, where this amide takes with the PBOAC helper. So first there's one acetic acid is eliminated to form this intermediate. Next, this reacts with RNase to react with the acetic acid to form this one. Then PbHA2 is eliminated to form this intermediate. From here, from this intermediate, upon reacted with the methanol to form this one. Upon reacted with this amine to form this one. And here, the hydrolysis to give this amine, they are to react with the acetic acid to form this one. So this is the possible intermediate. The next question is the synthesis of the beta alanine. So beta alanine may be synthesized to the Hoffman degradation of succinamide. So here succinamide in presence of 1 equivalent Br2 and in COCH3 acetic acid to form this beta alanine, which is a Hoffman degradation product. So next, we will discuss about the Kupffer's rearrangement or Lawson rearrangement and the Schmidt reaction. The Kupffer's rearrangement and the Lawson and Schmidt rearrangement consider next provide the means of the degradation of the carboxyl to primary amine containing one less carbon atom and Br genetic similarity. In the Kupffer's rearrangement, the key step is the thermal conversion of the acyl azide to the isocyanate. These acyl azide are usually prepared by the acting the sodium azide on acid chloride or by the acting the nitrous acid upon the hydrazide. So this acyl azide is formed upon the reaction of the acid chloride which is sodium azide or this hydrazide take place with NaO2 HCl to form this acyl azide. So azide must be treated with caution as it's a decomposite solubility. The sequence is very useful to preparing isocyanates, which may be carried out under non-aqueous condition. Nevertheless, the usual of course will event subsequent hydrolysis of the isocyanate to amine. So this chloride reacted with acetylide, this react with this benzene to form this isocyanate. So this under the hydrolysis to form this amine intermediate. So again the ethyl, this one react with this hydrazine to form this one. Then it is open react to the Na2HCl from this ethyl intermediate that react with the benzene. So benzene and heat this one isocyanate to form the intermediate form. Upon hydrolysis, it is found to form this aniline product. So during the hydrolysis, the isocyanate, the product amine may react with the isocyanate to form to may yield an in a disubstituted area, which is less successful to further hydrolysis. So this isocyanate is hydrolysis to form this amine that may be react with this isocyanate to form this in a disubstituted area. To solve this problem, acyl are allowed to undergo rearrangement in hot tert-butyl alcohol to yield an ethane derivative. This ureathane derivative on treatment with the CH2SO to get an amine. Thus, the Lozen arrangement refers to the conversion of the hydroxamic acid to the isocyanate on treatment with the strong inorganic acid, or the conversion of O-acyl hydroxamic acid to isocyanate on treatment with base. As reaction is normally carried in water, the process furnishes the amine directly. So the Lozen arrangement, here this one upon treated with influence of HCl or the base to form this isocyanate when upon the hydrolysis to give this amine product. The reaction is mechanistically similar to the fructose arrangement. So here first the protonation occurs, then upon elimination of water to form this intermediate, which react with hydrolysis to form the amine. So hydroxamic acid may be prepared. The action of the hydroxyl group amine on ester or acid chloride. However, the relative difficulty to obtain the hydroxamic acid is used less frequently than the fructose-Smith arrangement. The commonest version of the Smith reaction involves an acid catalyzed addition of the hydroxyic acid to a carboxylic acid to furnish the initially a protonation acetylide. This subsequent undergo rearrangement to form this isocyanate, which is then hydrolyzed to decarboxylate to the amine. So this acid reacted with this ethyl and upon the H2SO4 to form this isocyanate with hydrolysis to give this amine intermediate. So effectively, the rearrangement step is same in the fructose arrangement. Thus, this is an example. This acid group is converted to this amine group. So the product is obtained in the retention in configuration, which proves the intermolecularity of the reaction. Although the rearrangement step is the same as the fructose arrangement, it is only in the means of generation of acetylide that this sequence differ. Here the formation of protonated acetylide is believed to be proceed via the intermediacy of the acyl cation in the following way. So upon protonation first from this one, then the protomerization this one. Next this intermediate is formed. Next this one to form this one. So here the formation of the acyl cation is informed the RTS of the reaction. So in this connection, it may have informed that the formation of acyl cation is accelerated by the presence of bulky group on the carboxyl carbon. Thus with acid, thus the acid has to undergo Smith reaction faster rate in comparison to this. This is actually case during the mixed reaction if the formation is not observed, since the product amine is fully protonated in the strong acid. So thank you.